Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one focuses on problems solved by using the conservation of energy principle. What is the conservation of energy principle? Well, basically if there are no non-conservative forces doing work, well, what does that mean? It means forces other than the forces in a stretched string or due to gravity, then energy is conserved, and we have that the final energy is equal to the initial energy, where the energy is the sum of three parts: kinetic, gravitational potential and elastic potential. Let's look at this problem, essentially the bungee jumper problem. A bungee jumper of mass 5 kilograms is perhaps not terribly realistic, but the principle is exactly the same. A massive object of mass 5 kilograms in this case is attached to one end of a light elastic string. The natural length is 4 meters, the modulus 150 newtons. No problems with units there. The other end of the string is attached to a fixed point O. That would usually be on a bridge. The object, the bungee jumper, is held at O and then released from rest. So the bungee jumper falls freely until the string goes tight, the bungee goes tight, and then as the bungee extends, the increasing restraining force finally brings him or her to rest. So we're interested in the lowest point reached by the object in the subsequent motion. Clearly that's a very important calculation for setting up bungee jumpers, as you don't want to have any fatalities. So let's look at the force analysis. There are only two forces acting: the tension in the string, albeit that's zero when the string is slack, and the gravity, which is 5g. Now both those forces are conservative. That is to say, when they do work, we can calculate it by using a potential function. So let's do an energy analysis then. We'll start off by saying that the gravitational potential level 0 is at the base of the foot of the fall. So that's where the potential energy is 0. So initially starts from rest, no kinetic energy. Starts at a height of, well, that's what we're trying to find. So let's call it h. So h is down to the bottom. If we've got a mass of 5 kilograms and a gravity of 9.8 and a drop of h, that's going to be our potential energy. The elastic potential energy, initially the string is slack. Now the kinetic energy, well, if at the bottom there is zero velocity, that's the whole point about saying that it's the lowest point of the fall, that will be zero. The gravitational potential energy will also be zero, but we will have the elastic potential energy, and that will come from the term lambda x squared over 2L, which in this case will be the 150 for the modulus, times the extension which we're trying to find. Now be careful, the extension is not actually h, it's h minus 4, because the natural length was 4. And that's got to be squared, and we're dividing by twice the natural length, which is twice 4. So we're going to total these three, well, that's pretty trivial, isn't it, and total these three and then equate them. So here we have exactly what I said, just summarized, and we have the conservation of energy stated like that. Now, forgetting everything else, that's just a quadratic equation, so we can analyze that quadratic equation in the usual way. We've got, there's a term gone missing there, I don't know quite how that's happened. An 8 is missing in there, we'll put it back. So we expand the brackets here, and we multiply both sides by 8, so we end up with 5 times 8 times 9.8, which is 392. Now there'll be some tidying up. We want everything on the left, so the middle term here will interfere with this one, so we expect something quite different to appear. So there we are, 158 squared, etc. That's the quadratic. We solve that using the formula, and we'll get two answers. Right, now what are we to make of these two answers? Well, what we can certainly say is that for the problem that we've got, h has got to be bigger than 4. It's got to be a fall that's greater than the natural length of the string. So we can exclude the 1.89 and take the other one. So there we are, h is bigger than 4, so the lowest point is finally a depth of 8.79 meters. There's the question answered in context with the units. Now let's look at something further on the same thing, this time horizontal motion. An object of mass 0.5 kilograms this time is attached to one end of a light natural string. That's just what we'd expect. Natural length of 40 centimeters. Aha, careful, that's got to be 0.4 meters. And the modulus of elasticity is 180 newtons. The other end is attached to a fixed point on the smooth horizontal table. It's a smooth horizontal table, so there won't be any friction. There'll certainly be a normal reaction, and there'll certainly be weight. But both of those two won't act to do any work. So in the force diagram below, I've drawn it down here, there's a tension in the string, and I haven't put anything on the other two arrows because they don't come into the problem at all. We don't have to involve friction, so we don't need to know what the normal reaction is, and both the normal reaction and the weight do no work because they're at right angles to the direction of motion. So it's all summed up by that tension force. That's all. That's the only factor that we need to consider when working out the energy balance. Now the right-hand diagrams try to summarize the information in the question. The initial configuration has the extension of 50 centimeters split into the 0.4 and the 0.1. I'm already anticipating that I'll need the extension for the energy expression, and in the second case we have a velocity but nothing else. So we're now set up to do our energy audit. So there's the information again summarized. The energy audit comes from the stretched energy in this position but no kinetic energy, and the kinetic energy in the second position but no stretched energy. So when we do the energy balance, it's basically going to be a matter of equating those two terms. Now from the question we got that the modulus of elasticity is 180, the natural length was 0.4 meters, and the extension was 0.1, and the mass was 0.5 kilograms. So if we use the initial energy as the final energy, what we'll end up with this is that equation, which solved first to get v squared, just a rearrangement, and then we need to take a square root. V is that value. Well, is it plus or minus? Well, we know which way V is going. It's going to the left, so we can interpret it appropriately there. So we take the square root, having put the numbers in, 180.1 squared, etc., and it works out rather nicely as just 3. So we can answer the question that the speed at O is 3 meters per second. That's the answer in context with the units. Well, that brings this presentation to an end. The next one will work further on energy, but this time involving problems where the work done has to be calculated as well.